So what we're dealing with is, I think I showed y'all the trainer. I showed y'all the trainer already, right? Huh?
Mm-hmm.
And this thing was, the lab is written around this trainer, but they wanted you to wire up everything that's already in the trainer. So we're going to leave out a lot of the lab so we can get through with a lot of stuff. And this is what we're going to do. We're going to get familiarized with the trainer. That's basically what this is. The HCs, these are CMOS. These guys are susceptible to static discharge. They can be hurt. So what that means is that I don't give these out until you're ready for them. And they'll come into, we keep them in static foam. We'll talk about that later on. Static foam is a special type of foam. It's usually black in color that we can use to prevent static buildup on anything, any device that's susceptible to damage with static discharge. So we give these, and when you need them, you'll come over there, and I'll give them to you. So what we're going to do here is we're going to, and y'all need to read the write-ups too. We're going to deal with some. This talks about. This is a really standard circuit, and we're going to modify it a little bit. Let's see if I can find the modifications so I can explain to you. So what we're going to do here, this is really complicated, is that in our trainer, this is inside the trainer and this is inside the trainer. So what we mean is you're not going to wire up any of this stuff over here, and you're not going to wire up any of that stuff right there. So really on this, this is not a circuit you're going to build. But if I was to wire this up, you would take wires and run them from the switches to the LEDs, just to see how they work, right? Does that make sense? So that's why up here, a lot of this stuff on the required parts have been marked out, because we are not going to build our LEDs because they're already in the trainer. We're not going to build the switch circuit, and we'll talk about why we have to do it like this later on. So this is the first thing we're going to do. What type of gate is this? This is a logic gate. What type is it? It's a diode logic gate. What is it? Huh? Huh? Huh?
No,
well, what I do, I come up here. Well, it can invert, right? You understand? So these guys can't invert. So there's no way in the world it's going to be an AND or an OR. So it's got to be an AND or an OR gate. Well, what I do is I come over here and put a plus on here, right here. I put a plus right there and see what happens. Well, if I put a plus right there, that puts this guy's pointing toward the plus. This points, and it's forward bias, so the plus comes through, right? If I put a plus right here, it comes through. If I put a plus right here, it comes through. So the only way I'm going to get a low out is if I have no pluses over here. This is an OR gate. 3-input OR gate. Now, if I was to take a transistor inverter and put it on my output, it would be a NAND, it would be a NOR gate, right? Then I would have a type of logic called DTL. This is an OR. Yeah, we can't get any inversion with these diodes. Diodes do not invert. Transistors will, but diodes won't. So anytime you see diodes wired like this, anytime you see multiple diodes wired like this, these are not in parallel. People want to say they're in parallel because the outputs are connected together. If they were in parallel, the inputs would be connected together too, right? You understand? So to get something in parallel, the inputs and the outputs have to be connected together. So these guys are not in parallel. They're not in series either. They're individual inputs, right? Y'all understand that? So what we're trying to do is, so I know this is either AND or it's an OR. So what I do is I just start playing around with it. And I put a plus over here. And I know if I put a plus, it gets forward biased. So I've got a plus on one of them. I got 2 zeros. That plus right there gave me a 1, so it can't be an AND gate. Because an AND gate don't say one of them. It says what? All of them. All of them have to be high. So if I put a plus right here, it's going to turn this guy on. If I put a plus right there, it's going to turn that on. So this is an OR gate, a 3-input OR gate. And so we're going to build this. So I give y'all that the diodes should be in there. If they're not, let me know. And then it shows y'all how to identify the cathode and how to identify the anode. I give y'all the symbol right here. So y'all okay on that? This is a transistor switch, but this is a function that we use, and unfortunately we didn't cover this. But what we're going to do is we're going to put AC right here. So we're going to set up our function generator to give us AC. So the function generators, by the way, are in the storage over there on the shelf. So most of our stuff's on the back shelf, and they're down toward the bottom. Okay. And then the leads that we put on, it's got, my camera's still up. So you'll see a brown, one of these brown trays in there. One of them's labeled scope probes and function generator probes. This is a type of connector we call a VNC connector, which is a quick disconnect connector. And if you look at the connectors, so these guys have two stobs on them that focuses in. And then this guy's got two holes in it where the stobs line up. Y'all see right here on the side? And then it's got angled on the side. So what we do is we put it on, we spin it around to the stobs line up, then we push down and lock it around down. And it's spring loaded too. So this is a quick disconnect connector. This is the same type of connectors that we have on our scope right here. These are called BNC. Anybody know what BNC stands for? It's British Naval Connector, what it is, BNC. So British is actually the ones that came up. By the way, so what we want to do on this one is we want to put it on output, right here, output. So my function generator is a little more complicated than the one you got, so it's pretty easy. But we hook this up with the output, so, and then here's our connectors off that connector. So the black lead is truly ground, by the way. This is ground. Grounds through the power supply. And then this right here would be the signal wire right here. Okay? And so this is our function generator right here. So we got plenty of them in there. They're on the, like I said, is all the stuff we're going to use is on this back shelf against this wall right here. So what we're going to do is we're going to set up an AC waveform, and then it says it's going to be 1 kilohertz. So how are we going to do that? Oops, wrong thing, Rich. So right here we got two knobs. Let me raise this up a little bit. See if it's going to focus. If it's not. These two knobs right here are labeled frequency. We're using a sine wave, so these buttons right here tells us what type of waveform we're going to generate. This says a sine wave, this is the pulse waveform, and this is the triangle wave. So you can set it up for a watt, sine wave. Okay. Now what you need to do here is set your scale. So you can't get 200 we can't get 1 kilohertz out of this guy, so you're going to select what? 2 kilohertz. You're going to come over here and turn this knob until it says what? So this is the course adjust right here. It's labeled course. So now I've got 1023. So what would I do? I come over and adjust the fine until we get 1000 hertz. Or real close to it. Are you okay? So now I have 1000 hertz of sine waves coming out this thing right here. Now we can see this on the oscilloscope. So what would be the period for 1000 hertz?
What would be the period for when
For 1000 hertz. One millisecond? Everybody agree with that? Well, I said 1 millisecond. Agree with him? Everybody agree with him? I got to open somewhere, guys. I gotta figure out what's that. I think it might be right here. Okay. So I'm going to stretch it out as far as I possibly can, which is this is it, right? We'll come over here and I'm going to move this until it gets on a vertical line. I have it on, I have 1 microsecond per, I have 100 microseconds per division, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 8.5. That looks, oh, I'm sorry. I think so. That don't look like 1,000 Hertz. So 1 milliseconds, correct. Okay. So I'm gonna move my position again and get it where I want so I can see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 100 microseconds is 1 millisecond. Now the problem is that this is AC, but we don't want to put AC on the integrated circuit. So this is pretty common. So what we're doing here is we're setting up a common circuit that's going to take AC and convert it into a pulsating DC waveform. And I don't have anything to write with. I should draw the circuit on the PowerPoint. But what happens, notice, here's the negative, right? Here's the positive. So when I put a positive waveform in here, the diode is reverse biased, right? Y'all see that? By the way, that's a symbol for an AC, a voltage source. This right here is going to be our output. I don't know what we're using up here. We can put anything. So when the input does this, this is an NPN. That's going to, this diode is going to be reverse biased. Y'all understand that? So what it's going to do is it's going to come over here and saturate the transistor. So the transistor is going to cut off, right? I'm sorry, it's going to cut on. If it cuts on, it drops 0 volts, so that means the output would be 0. It's an inverter, so when the input goes high, the output goes low, right? But what's going to happen when this thing switches negative? Now what happens is the transistor can't have a big negative potential on it. So what happens when it gets negative, it forward biases this diode. So this only goes to a negative 0.7 volts. So it's not going to hurt the transistor. This resistor drops all the voltage. This guy right here sees a low, so the output will go high. And then it's going to saturate. And then when it goes low, so what we're going to do, and here's 0 volts right here. So this right here is going to take a AC sine wave and convert it over to a digital pulse stream. That's got a period of 8.6, 8.7 milliseconds, and a duty cycle equal pretty close to 50%. We do this a lot. If I wanted to time off Alabama Power, Alabama Power runs at 60 cycles per second, 60 hertz, and it's beautiful, perfect. So like we said, most of the time, if you got any clocks that when power goes out and it comes back on, you've got to reset them. There's a pretty good probability that those are timing off Alabama Power. Well, Alabama Power generates AC, but my digital works off of DC. So what we'll do is we'll have a device called a transformer that steps this down to about 6.3 volts, and then we'll run into this circuit right here, and then we'll use this right here to generate our time. Now it's moving at 60 cycles per second. We want it to get to 1 cycle per second. So later on, we'll look at devices that we can actually divide frequency with, frequency dividers. So what I would do is I would bring this in and bring it into a frequency divider. I bring 60 hertz in, I get 1 hertz out, and we use that to run our clock. And it's really accurate too. Alabama Power is extremely accurate because frequency, changing the frequency is more drastic than the voltage because of something called X of L, which is the impedance of the circuit. So if they don't put exactly 60 cycles, that means their transformers don't work right. So everything in that system, that power grid for Alabama Power is designed for 60 cycles. Plus, if they didn't put out 60 cycles, a lot of motors out there wouldn't run at the right speed. So this circuit right here is going to convert AC into DC, which is pretty neat. And this will be your first opportunity to use a scope. Anybody ever use a scope in here? So that's the way we should have got partners when we partner up, but it's too late now. So any questions? So let's look at what else we're going to do. So we're going to do this guy. It's an inverter though, right? Let's go through the rest of the lab, make sure we understand this. So we're going to hook up that circuit. Make sure you hook up the diode. By the way, anytime you hook up a circuit, what I want you to do, y'all still new at this, and I want y'all to get me to check them off before you power them up. Because if you accidentally put that diode on this side, you're going to short out the negative alternations, and it could mess up my function generator. Now this is the circuit I'm talking about. All we're trying to do is see how the switches work on the trainer. So the switches work on this kind of basic principle right here. So what we got to understand that a 0 is not a nothing. A 0 is going to be a common. So that means our switch has to be able to switch between a true high and a 0. So what we do is we use these devices right here called pull-up resistors. You know, see why they're called pull-up resistors? Because they pull the line up. So if this switch right here is closed, then it connects ground right here and we get a true 0. If I open up the switch, then there's no current flow right here, right? You understand that resistor doesn't drop any voltage and we get a true high. So this is real common in digital because digital a 0 is not an open switch. A 0 is a common, right, or a ground. Y'all understand that? So this is very common on switches in digital. Is use a pull-up resistor to give us the high and then use the switch to give us a what? Give us a low. This is exactly the way, later on we'll look at the schematics on the trainer, and this is exactly the way the trainer does it. So just about every digital circuit I've ever seen that uses a switch to give a 1 and a 0 is wired with this circuit right here. But this is inside the trainer, right? You understand? So if it's inside the trainer, you don't have to do what? You don't have to hook it up. The LEDs are in the trainer, so you don't have to hook it up. So what you're going to do is you're hooking this up to see what position of the switch gives you a high, what position of the switch gives you a low, what the LEDs do over there. Does that make sense? And you're going to connect all 8 switches. This only shows you to connect 4. You're going to go ahead and connect what? All 8 of them. Are you okay there? This is real easy, guys. Then we're going to hook up our first inverter. 7404, 74 LS04, doesn't make any difference. So the main number is 7404, and then what does the center letters give us? What does it tell us about the integrated circuit? I'm listening. 74, this is a 7404. LS04 is what the lab calls for. But in this experiment, it could be anything. So what's the difference between a 74 LS04, a 7404, a 74 HC04? The pin out there, not. They're all hex inverters. What those letters give you is the speed power characteristics of the chip. So as we go along, we'll learn the difference between a 7404 and a 74 LS04. For this lab right here, it makes no difference. If you got a 7404, it would work. If you got a 748C04, it would work. If you got a 748CTO, it would work. If you got a 74 ALS or Fairchild call, there's a 74 FAST, fast. So you can guess that sucker is what? Fast, yeah. So that's their version of the AST. So first thing you're going to do is you're going to assign pin numbers before you hook it up, right? We talked about how to wire these up last class. Don't forget to hook up the power and the ground. If you got your textbook, hopefully you sit with somebody that has a textbook. You're going to look at what we call the pin out. It's on the inside cover of your textbook. You got a 7404 in there, right? What's the power pins? If y'all look real quick, what's the power and the ground pins? What's that? Ground is 7, power is 14, right? See that? Yep. Yeah, power is 7. Power is 14. 7 is ground. And then we got, it's a hex inverter, so we got 6 of them in there. So this is the first time. So first thing you're going to do is what? So normally on schematics, they take for granted that if you're working with these things, you understand these suckers have to be powered up to work. So when we look at all our digital connectors, our digital schematics, they never show the power pins on the IC. Never. Or hardly ever. I've seen some of them that does. But these suckers will not work if you don't power them up. Y'all understand that? So here, when we put a high in, we should expect a what out? It's an inverter, guys. High in should give me a what? Low out. Low in should give me a what? I am. Good. Now this is where it gets a little complicated, and I don't know if y'all get here tonight, but what we do when we get here, we'll just come back over here and explain this, because I know y'all get bored of me talking, so we're going to go ahead and go lab. So what you need to do is finish up lab number what? 1. If you have some parts that's missing, I think some of y'all didn't have the 74154, which is the 24 pin thing. I can go ahead and give that to you tonight. Some of y'all didn't have the 74 LSO100s, the quad 2 input NAND gates. So I can give those to you tonight. All right, guys, let's go to lab.